हेलो, हेलो,
जी सर, हेलो, गुड
हेलो।
मॉर्निंग सर।
गुड मॉर्निंग सर, गुड मॉर्निंग सर। डॉक्टर साहब आए हैं, रुपिंदर सर?
जी जी जी, वो तो ज्वाइन करके सर।
अच्छा, डॉक्टर साहब, सर गुड मॉर्निंग सर, गुड मॉर्निंग।
Sir, good morning ji. Very good morning
Good
to all
morning
of
sir,
you.
myself Sanjeev Gupta. I'm an associate professor and head of mechanical engineering department, Government College of Engineering and Technology, Jammu. And I'm also the alumni of NITTTR,
Okay, that is great, sir.
2005 batch.
Okay.
PG.
Nice to hear from you on.
Then our head of department was Laroya sir, Subhash Chandra Laroya.
Yes, yes.
And then he became a director. Then बनवैद सर आए थे मेरे ख्याल, HOD.
Okay.
दामी सर, बनवैद सर, पावला सर.
हाँ जी, हाँ जी.
आप 2010
हाँ
के
जी,
बाद
हाँ
ज्वाइन
जी.
किए ना, लगता है मेरे. जी सर. बाकी सारे वो है, वो क्या नाम, राव सर हैं, PS राव.
Yes, yes.
वो हाँ सारे हैं सर. 2 मिनट सर वेट आपको थोड़ा सा करना पड़ेगा. मैं सारी क्लासेस ऑफ करवा के बच्चों को कहता हूँ जरा करेंगे.
हाँ, not an issue.
जी
Please
सर,
take your time.
जी सर, जी सर, जी सर. प्रदीप सर, हेलो.
हेलो.
हाँ प्रदीप सर, ये इसको फोन करो पवनदीप को कि
जी सर.
3rd की क्लास उसने ज्वाइन करवानी थी 10:30 पे.
ठीक है सर.
फटाफट सारी ज्वाइन कराओ. इसी तरह एमटेक के जो है, PG के हैं जो, वो आदित्य सर को करो. साहिल सर आए हुए हैं?
साहिल साहब भी नहीं है. जो
भी टीचर है हमारे.
हाँ जी सर.
साहिल, आदित्य को एमटेक 1 ऐड कराओ, एमटेक 2 ऐड कराओ. और ये प्रदीप करता है फोन इसको, पवनदीप को. 3rd सेमेस्टर 5th सेमेस्टर सारे जो फैकल्टी मेंटर्स है ना, अपने बच्चे कराओ ज्वाइन. तो जो लोग नहीं ज्वाइन होते हैं वो फिर YouTube लिंक पे चले जाए. ठीक है, ये आप जरा ये कोऑर्डिनेट करो जो टीचर्स है ना हमारे.
जी सर.
ठीक है सर.
Once the Google Meet is full, then all shift to the YouTube. Okay.
ओके सर.
जल्दी कराइए यार, सर वेट कर रहे हैं. चलिए जल्दी कराए हैं. Amresh sir, we will start within 5 minutes.
Okay sir, no issue.
बेटा ये मनदीप कौन है, किसने शुरुआत करनी है? वेलकम दोहा। मनदीप, हेलो मनदीप, मेरे सारे 1 मिनट वेट करें यार, मुझे लगता कोई प्रॉब्लम आ रही है कहीं। मनदीप, मनदीप am I audible? हाँ करो, ऑन करो, वेलकम करो, चलो। मनदीप कोई प्रॉब्लम आ रही है क्या दोहा को ज्वाइन करने में?
सर मैंने कर लिया ज्वाइन, सॉरी
हाँ
सर।
दोहा स्टार्ट करिए बेटा। और मनदीप एक मिनट दोहा, मनदीप अभी आप अपना देखो, जो लोग नहीं करे उनको यूट्यूब लिंक ज्वाइन करवाओ। हाँ कर दो, यहाँ पे नहीं आप करवाओ, पीछे बैकग्राउंड में रख के कराओ यार, ठीक है जी। ओके दोहा स्टार्ट प्लीज।
We are made for goodness, we are made for love, we are made for all of the beautiful things that you and I know. We are made to tell the world there are no outsiders, all are welcome. A very good morning to all of you. I, Duha Faisal from 5th Mechanical Branch, is the host for today's event. I am thoroughly pleased to witness you all here in this seminar. The ACIC-RISE Association Incubator, funded by Niti Aayog Govt of India, in collaboration with Royal Mechnocrats of Govt College of Engineering and Technology, Jammu, they organized a seminar 3D printing under the aegies of Azadi ka Amrut Mohatsav. It's my privilege to welcome the guests who are present here to attend this seminar. It gives me immense honor to welcome Dr. Sameeru Sharma, Principal GCET Jammu, for gracing the occasion with her valuable presence. I welcome Amrut Kumar, Practical Manufacturing Engineering, ACIC-RISE Association. Sir, an enthusiastic teacher and mentor for emerging startups. He has facilitated many research projects and got 25 publications in reputed journals and got 1 patent grant and 8 published to his name. I welcome Mr. Sonu Kadam, young professional, aim at ACIC-RISE Association. Sir has pursued master's degree in mechanical engineering with specialization in manufacturing engineering from IIT Ropar, Punjab. Area of expertise: 3D printing technology, surface engineering, powered metallurgy, startup, entrepreneurialism, idea, IPR. Now I welcome Engineer Sanjeev Gupta, Coordinator, Royal Mechnocrats Club. Thank you, sir, for being a part of this event. Without you, it could never have been possible. On behalf of the institution, I offer regards to all the guests and the people joining us. I pay my regards to the guest speaker, Dr. Rupinder Singh, Professor Head, Mechanical Engineering, NITTR, Chandigarh. Sir has received his PhD degree in mechanical engineering in 2006 from TIET Patiala, Masters of Technology in 2001, and Bachelors of Technology in 1999 from Punjab Tech University. He is chartered by Institutions of Engineers and AICT Young Teacher Awardee, DST Scientist Awardee, UGC Research Awardee. Currently, he is a professor of the Department of Mechanical Engineering, National Institute Teachers Training and Research, Chandigarh. Thank you so much, sir, for accepting our invitation and coming over for the seminar. Now, I like to welcome Dr. Amrish Kumar so that sir could share some of the valuable thoughts with us. Over to you.
Thank you, dear students from Technocrats Club, Jammu, Royal Mechnocrats Club, in fact. A very heartiest welcome to Professor Rupinder Singh ji, Head Mechanical Engineering Department, NITTTR Chandigarh, and very thankful to you, Professor Gupta ji, for offering all kind of support to organizing this event on behalf of ACIC-RISE Association. which is a incubator funded by Government of India, supported by Government of India, Niti Aayog. Uh, I think it's already, we are late for this event, probably, but still I will take 1 minute or 2 minutes. Pardon for that, sir. So ACIC-RISE Association is a major objective is to promote culture of innovation, entrepreneurship in this region, in Chandigarh region, J&K region, Himachal region. Although we have some of the incubator in the past, but here what we are like mostly uh, wish to mentor those kind of startups who take the community problem as challenge. People in this northern part, I would say, we are struggling with lot of problems. If we talk about agriculture, if we talk about climate conditions, if we talk about this availability of water resources, depleting resources, water resources, if we talk about health issues that we are facing right now, so technological advancements are going to be the key to take these challenges. So this incubator is basically welcome those startups, those innovation ideas who wish to take on those challenges. Where like we can say that India is self-reliant, India is Atmanirbhar. We are like as good as USA, as good as Canada, as good as any developed country. So we are on that process, but still there are a lot of challenges ahead. So the key factor to face those challenges, to overcome those challenges, that we have young people of India, Youngistan, I would say, lot of young people. If we talk about this index, most of the young people living in this country, and they're all blessed with lot of talent, lot of wonderful ideas. The only thing they need a platform where they can like go through that platform and go to perform their ideas, uh, realize their ideas, what they are planning about. So this incubator offer all kind of support. If you have any kind of innovative idea to solve any problem, so we offer all kind of patent support here. We can protect your intellectual right. We provide mentor support. We provide industry connect, where you can see whether your product is really beneficial to the society, or if you have that product, so can you get that number of you can get that number of orders so that you can survive in the market. Then we have a lot of funding agencies who wish to pay funds to different startups having some wonderful ideas. Obviously, technology we cannot think about. If we talk about current scenario, if we talk about the very biggest problem in the industry in the this country is unemployment, and the manufacturing sector is witnessing lot of number of problem in India. And if we take a global picture, China is taking a very edge, very on the topmost position in the worldwide. If we talk about China, they are doing wonderful things, wonderful innovations. They are miles away from us in terms of technology. We are very reluctant to adopt these kind of technologies. Uh, for example, 3D printing is one of that emerging area where we can do a lot of things for the society. We can come up with different number of solutions, different number of prototypes with this smart technology. So I am not taking too much time. So if you, I wish this session going to be very fruitful to you. I request today's guest, main guest, chief guest, Dr. Rupinder Singh ji. He has a very great expertise in this areas. He is a very renowned speaker, and he has got very good marvelous research record, and he's a really role model for us actually. So I request sir to share his valuable thoughts, his experience in this very emerging field that is 3D printing. So I hope this session going to be wonderful to all the participants. Thank you, sir, for joining. Thank you.
Thank you so much, sir, for enlightening us. Schedule of the seminar will focus on the topic. It will include more issues to address the full aspects of the topic. I wish the seminar enlightens us all and provide us with approaches to deal with the problem. Now, I am profoundly delighted to take an opportunity to welcome our guest speaker, Dr. Rupinder Singh, so that Sir could enlighten us with valuable information regarding 3D printing. Over to you, sir.
Thank you for giving me an opportunity. I'm really thankful to the principal, Dr. Sharma, head of department, Mr. Gupta, then Dr. Amrish from RISE Association, and Professor Kadam for coming up with a wonderful idea of supporting the startups in line with the Government of India initiatives. I hope that these type of initiatives are really helpful in making the country self-reliant and as a technocrat, now it's our duty to come up with some solutions which can help our country to come up with the new ideas, new products which we can launch in the market first, and then we can have a lion share in the market. So keeping these thing in mind, I would like to share my slides, and then we will have a discussion on how this 3D printing can really help us in developing new products which can be in line with the some of the development aspect of the country. I hope my slides are visible.
Yes, sir.
Okay, so the discussion part which we will be taking today will be on 3D and 4D printing. It is expected that in coming 5 years, this will be the part of the main manufacturing, not in the world only, but not in the India, but across the globe. So why we are interested? I have just some signature slides to put the point in front of you. Now, if you see the Niti Aayog website itself, which is earlier it was known as the Planning Commission, right? So it is saying that India's contribution for the GDP, specifically from the manufacturing sector, is stagnant to the 15%. And we normally want to compare with the other world power like China, where this contribution is around 34%. And if you just do the Google and see this data, it is representing that there seems to be some policy failure as regard to contribution of the manufacturing sector is concerned. One of the things that I observed while searching through the website only, that sometimes we lack in the really innovative products. So we need to come up with a new product with value added features, so that this can be really a world first product. Then it will have a lion share in the market. Because after this some new product is there, then a lot of people, specifically in our country, we used to make copy of that. But now that time is over. Once you are copying somebody else's product, now we have to come up with really an innovative product. The problem is not new. The government of India is taking it as a challenge. And in 2004, the government of India set up a national manufacturing competitive council, which was headed by the group of ministers. And even in 2006, the prime minister at that time, he concerned his views. He has shown his concern over the contribution of the manufacturing sector, which is 12 to 14%. It must be increased to 25 to 35%. And if you just see the Planning Commission website right now, Niti Aayog website right now, it is saying that we have to increase this contribution by 10% by 2025. Right? This is really a big challenge. If I have to make this contribution of the manufacturing sector higher, then a lot of things has to be explored. Not only the government, but some public sector people, private sector players, they are also showing their concern in a similar way, that if you increase this contribution, this will be really nice for the country. And it is expected that if we increase the contribution of the manufacturing sector by 10%, there will be 100 million jobs for our countrymen. There are some problems due to which this is actually not being done right now. These problems are like inadequate infrastructure. We have a problem with the infrastructure. Nowadays, the government is, paying a lot of interest. It is, developing so much road network, rail network, all these type of things. But still, we have a problem with the infrastructure. We have the finance issues. We have the issues like land acquisition, labor laws, and there are so many difficulties due to which some large players are not coming to our country, right? So problems are there. Now, if there are problems, should we stop or we can have some alternative solution? Now, to understand the alternative solution, a lot of deliberations were going across the country, and in one of the deliberation between CII and government of Andhra, they came up with a very novel way that innovation in the product and process, this can be the key driver for the growth in the manufacturing sector. Now, this is the key point across which our whole, this discussion will going on. So I need to innovation in terms of product or innovation in terms of the process. If I do this, then definitely this can be really helpful for the growth in the manufacturing sector. I give you one example. Like if you go to some of the tourist place, normally we used to buy some souvenir as a token of remembrance. Right now, if that's just a simple souvenir, it may be some keychain or something like that is really innovative. It can do more than one function at a time. Then this will be definitely an interest for us. As a typical mechanical engineer, we are exposed to the concept of method engineering, work study, work measurement, these type of things. And we are exposed to understand the concept of principle of motion economy. So which is saying that if with a single tool, I can do the multiple jobs, it helps me to save the time. So that thing can be actually applied in all the innovative products, which can be of some interest for the different people. So that is the idea of developing some new product, innovative products, and to solve the problem of the countrymen. Okay, before I start my presentation further on the 3D printing, this is the just last slide about the information. If you see the third-party data for our country, this is by Thomson Reuters, which is now overtaken by the Clarivate Analytics third-party data from US. It is saying that India's share for the engineering research was 4.3% in 1981, which was reduced to 2.2% in 1995. And presently again, if by 2010 it was again to 4.25%, and if you see to 2020 data, this is again less than 5%. That means for research in engineering, for the 95%, I am dependent upon the outside world. If I just compare the similar data with China, Korea, Taiwan, these countries are doing much better than us. We normally says that we are good in software, but our contribution at international level is just 2.4%. So the from here, we can just imagine there is a big need, there is a big requirement for the country that we innovate, come up with a new product. We must have our own IPR, and we launch the product first so that India will get a lion share in the market. I think this can be really one of the greatest contribution from the technocrat for the country. Okay, now coming to the business, I have been assigned a task to talk about 3D printing. So why I am correlating this thing? Because I am interested in innovation, maybe in terms of the product or in terms of the process. And for this type of thing, the 3D printing is one of the established route through which we can do these type of activities. This particular classification I have taken from Cheng and Chua paper. This was published in 2005, Journal of Advanced Manufacturing Technology, Springer. Now what it says, rapid manufacturing, then subdomain under rapid prototyping, we have basically three types of classification. The processes for rapid manufacturing may be additive in nature, they may be subtractive in nature, and there can be the combination of the additive and subtractive. For the subtractive manufacturing, we are quite comfortable. Like for the CNC machining, this is one way of rapid prototyping and finally contributing to the rapid manufacturing. This is very much known to us. Then in additive manufacturing, there can be the technologies which is based upon some liquid-based technology, which is based upon some powder-based technology, or there can be technology which is based upon some sheet-based technologies. And under their subdomains, there are so many technologies for the polymers, for the molten metals, then number of commercial technological names are there. And then there is a third classification, which is a combination of additive and subtractive. Normally, in different sessions, people talk about, okay, we are shifting from the subtractive to the additive. But my personal opinion is, in coming 5 years, we cannot eliminate subtractive technology, definitely, completely, but there can be a combination of additive and subtractive, because we are always interested in manufacturing as a cost-effective solution. But in next 10 years, the subtractive manufacturing may be 90% eliminated towards the additive manufacturing side. Here again, my aim for discussion is not to explain about a particular technology for the liquid-based, powder-based, or sheet-based, but to introduce the audience that these technologies are there. Now, if I am interested in really a good solution, a cost-effective solution, what sort of innovation we can do so that there can be some customization specifically for the reduction of the cost of the product. So here we are going for some of the technologies. Now for the beginners, like we have some of the students from first year or maybe up to master's level. Some of you may be knowing about 3D printing. I will introduce some of the basic part, and then we'll share some of the case studies which can be really helpful for making a useful product. So as you can see in this slide, I can have some data in the CAD file form. This data is which is a CAD file, is fed to the printer. Now this printer something look like a photocopier, but this is giving me output in the form of the 3 dimensions. So I'm getting a 3D printed object. So let me tell you how this actually started. In early 80s, the MIT researchers, they used basically a inkjet printer to come up with first commercial 3D printer. How actually, if you they develop, if you just see how my inkjet printer works, I have basically a nozzle through which some ink is spilled out. Now this ink, which is we call it as a cartridge, this moves in a XY platform in a Cartesian coordinate system, and I drop a defined quantity of the ink at a particular location, so I get a 2D object. So what actually they did at that time, in place of one nozzle, they put 2 nozzles. From one nozzle, some ink was being sprinkled, and from the second nozzle, some binder was being sprinkled. So layer of powder, layer of binder, layer of powder, layer of binder, so we get a 3D object. A very simple way of understanding the 3D printing. Just I am getting the third dimension along with XY. I am getting the thickness in the Z dimension, right? So that is the one of the basic 3D printer which was commercialized by a company called Z Corporation, and they earned a lot of money out of this. So I am working in this 3D printing since 2005, and at that time we purchased this machine which was costing us something around 65 lakhs. Nowadays the cost of the 3D printer has reduced up to even up to 10,000 rupees. You can get a good commercial printer. So basically how this 3D printing is moving. So I have a CAD file which is transformed into different cross sections which are virtual, and finally I am getting a 3D printed part. This is the another way to understand. So I am interested in some product like this. So I am doing some layer by layer manufacturing. So each successive layer bonds to the preceding layer, which may be melted, partially melted on a build platform till we get a finally 3D printed part. Again, the explanation is very simple. I can put the layers by melting or partial melting. I can have a situation where, layer by layer components are added using some binder, using some heat as an input, using some laser source as an input. So there are n number of technologies. Commercially, I will say 30 plus such technologies are available, and each have a different, domain of working. Now, going one step ahead to this is the idea of the 4D printing. 4D printing is basically the printing of the smart materials. This is again, there is nothing like the printing in the fourth dimension. This is the printing of the smart material in 3 dimensions only. But to add the fourth dimension as a function of time, what I am interested is, if I give some stimulus to my material, how this behaves, means whether it is growing in dimensions, whether it is changing some color, or there is some change in some functional capability of this type of material. That is the part of the 4D printing. I give you one example to understand this. Then we will see some case studies for 3D and 4D. Okay, the example is from the daily life. We normally face, we see the sunflower. Now you see the sunflower normally faces towards the sun. So once there is a sunrise, the flower is moving in, let us say, upward direction, facing towards the sun. So once there is a sunset, the flower faces down. So just imagine, as a typical mechanical application, I have some stimuli which is in the form of sunlight, which is helping me to have a up down movement. Then there is a movement of the earth around the sun. So we see there is some rotary or some angular movement of the plant or the flower, and it is always facing towards the sun. So this is basically a 4D. Now the flower is not growing, but it is having some controlled movement with respect to that stimulus. Now, taking the example from the typical mechanical engineering application, like we are interested in, let us say, the force measurement or the torque measurement in our conventional machining. So what we do is we take the help of the dynamometer. So if I see how the dynamometer works, I have a quartz crystal, right? So if I put a load over the quartz crystal, there is a change in the dimension. Now you release the load, it will come back to the original dimension. Number of times you put the load, number of times you release the load, so it can have a repeatability, and the dimensional change we can really control, right? So just imagine if I use these type of material for printing, and then that 3D printed part is exposed with a stimulus like a load. Basically, I can have a very beautiful application of this type of material. I give you one example for this. All of us may be knowing about a polymer called PVDF. This PVDF is a polyvinyl difluoride. If you see this polymer, it has a carbon-carbon chain, and alternative there are hydrogen and fluorine. Now, if I apply a high voltage or load to this type of material, the hydrogen, all hydrogens are aligned to the one side of the chain, and all fluorine are aligned to the other side of the chain, right? So this helps us in getting the conversion of the material from the alpha phase to the beta phase. So basically, in alpha phase, alternative hydrogen fluorine are there, and in beta phase, all hydrogen aligned on the one side of the chain and all fluorine on the other side of the chain. So this helps me in generation of some of the van der Waals forces, and we get a piezo effect. So this piezo effect in a 3D printed some functional part by the application of load is an example of the 4D property. So basically what we understand, this 4D is an extension of 3D. 3D printing becomes 4D when time as the fourth dimension is added to the 3D printing functional part. So what can be the reason of the smartness for this type of the material? The reason of the smartness can be the internal property, or these can be the external property. So under the intrinsic property, basically we call it as a autonomic system. And once I'm using the extrinsic property, this under the non-autonomic system. So autonomic means related to the automatic, like in case of the sunflower, this is something automatic. Then extrinsic, where some human intervention is required. Like there can be the properties like self-expansion and self-contraction, like the case of the quartz crystal or the PVDF. Sometimes I am interested in adding some external property to this type of the material. So this can be maybe through reinforcement or through the metamaterial. Now, for example, I am interested in increasing the thermal or the electrical conductivity of some polymer, because polymers are normally insulating in nature. So if I do some reinforcement, like the reinforcement of some aluminum powder, copper powder, or the graphene, this helps me to increase some of the electrical or the thermal properties into that material. So this is under the category of the reinforced material. Then there is a new concept in 3D printing, that is the use of the metamaterial structure. Our civil engineering friends, they are very comfortable in the metamaterial. We can also use this type of concept for reducing the weight of the component and getting the high strength. To understand this concept for the 4D, take the example of a railway bridge. So once we study about the railway bridge, we are exposed about the concept of the trusses. So in trusses, in basically strength of material class, all of you may be knowing, we are interested in some length of the link and the angle of the link, which is important for giving some strength to the final functional part. So similarly, here in metamaterial 3D printing, whatever the strength I am getting is not because of the strength of the material or the young modulus of the material, but I am interested in the particular length and the angle of the link, which helps me to generate a particular strength over there. Okay, I can also do some programming. It can be one way, two way, and multi-stage. Like my material is in state A, this is 3D printed. Then I give some stimulus, it changes to the state B. Then give another stimulus, it comes back to the state A. This is a one way of programming. Material is in the state A, you give the stimulus on, you give the stimulus off, it comes to the state B. So this is the another way of two-way programming. Like for example, in this case, the stimulus can be electric field or the electric current or the magnetic field, right? So you switch on the current, it changes to the state B. I give you one example to put my point over here. One of my collaborator is working on some telescopic leg. He's basically a surgeon in PGI who is working on the leg deformities. So basically, if you talk about the leg deformities, basically the two length of the leg are of different legs is not same, right? Now what we do is we cut one leg and put a telescopic arm. So as the patient is growing, to increase the length of the arm, basically what we are doing is we are using some magnetic stimulus through which that length is basically increased. So this is how you can control the 4D part as the two-way programming. Then there can be multi-stage programming. You have some material, some 3D printed part in state A, give some stimulus going to state A1, then another stimulus A2, then another stimulus. There can be multi-stages, but important thing is there should be repeatability, right? So the circle must complete. So with the different set of procedures with the different stimulus, it should be a closed loop structure. Okay, now I will introduce one of the very simple technology, which is a polymer based technology. The name of this technology is FDM. I will show you some of the application and the functional part that has been prepared by 3D printing, and let me introduce you how we can do the startup in these type of things. One of my collaborator in Italy, we are working on developing these type of the products, and we are providing this to the different manufacturers as a technology transfer part. So what is the technology? Let us understand the technology first. I have a polymer spool, thermoplastic spool. This thermoplastic material is fed to the chamber over here. So what sort of chamber it is? It is having some arrangement through which some wire of the polymer is fed to a region which I am calling as a liquefier over here. Here there is a heating arrangement from the inside, right? So some heaters are there. Then on this side I have a nozzle. So larger dia wire, normally the dia is 1.75 mm for the commercial printer, right, is fed to the mechanically fed to the liquefier where I have some heating arrangement. This can heat normally for the commercial printer in the range of 100 to 300 degrees Celsius commercially, right? And then once this wire is fed and heated through this, then I have a nozzle over here. The output wire that is coming from this side may be having a size of 0.1, 0.2, 0.3 mm, depending upon the dia of the nozzle that I have fed. Now this fine strand of wire which is coming from this side is deposited layer by layer over this surface. So as I am getting a thickness by this Z platform, this is coming down. So this is how 3D printing is executed using a polymer based technology, which in this case I am calling as the fused deposition modeling. So feedstock filament, thermoplastic feedstock filament. This feedstock filament is fed to the chamber, liquefier chamber. Then I have a nozzle over here. So layer by layer deposition. Commercially, if you see the dia of the wire, input wire is varying from 0.4 to 4.0 mm, but most common use size is 1.75. And depending upon the output fineness, I can have this as 0.1, 0.2, 0.3 mm dia over here. So I get a 3D printed part. Now, some of you may have a question why there are two different color wires over here. One is a dark blue color, another is little greenish in color. Now, the idea is there is a concept called build material. There is a concept of sport material. So, build material are normally oil soluble in nature, and the sport material are basically the water soluble in nature. So, what I am interested is, in this part, suppose I am interested in some cantilever type situation. Now once the wire will be coming from this head, right, so this will be at the temperature of, let us say, 300 degrees Celsius. So it need a base over which this protruded part can sport, right? So I need a sport material. So this water soluble sport material is there, so which is put over here, so that this final component is deposited over this. So once I have printed this component, then I will put it into the ultrasonic chamber where the water soluble part is basically dissolved, and basically in ultrasonic chamber I have a water at the temperature of 65 to 75 degrees Celsius. Then I have the transducer on the lower side. Normally 30 kilohertz is the recommended one, and I am doing the churning in the water with a pH value more than 7. Basically the basic solution is there, and I can do the the dissolving of these type of water soluble material and getting a final component. So this is how the 3D printing is executed using this type of the technology. Now I'm taking you to the case study of applying all these input so that I can develop my own feedstock filament and can sell it in the market as a startup. So what we did in this study, we used the material called ABS, and we use the material PA6. So ABS is one of the most widely used thermoplastic material. This is acrylonitrile butadiene styrene. This is polyimide, basically a nylon. Nylon 6 is basically extrusion grade of wire that can be extruded. And it has been reinforced with a banana fiber. and we try to ascertain their thermal, mechanical, and the morphological properties. Actually, once we started this work, we have one of the collaborator from Jalgaon, and he just explained us that in his area there are a lot of banana fiber as the agriculture waste. So we need to, come up with some novel solution that can be helpful in managing that type of the waste. So we explored a paper. There was a paper of Bahrain et al., which explained how to condition the banana fiber. So using that paper, basically, we prepared the banana fibers of 1000 micron length and the 100 micron dia cylindrical shape. And this was blended with the 5% by weight in ABS and the polyamide. How actually we did? This is the extruder, benchtop model extruder that we have used for the blending. So basically the ABS granules, which are the polymer granules or the polyamide granules, basically these were reinforced with the banana fiber. Here these are the intermeshing screws. Basically in this chamber there is a intermixing of this, and then on this side I get a very fine wire. That fine wire was prepared at some temperature like 230. The nozzle dia was kept over as 1.5, and we can control the torque or the RPM of these type of the screws. Then this was fit to the 3D printer, and this is an open source 3D printer of 200 cube size. I can print over here. And finally the tensile coupons as per ASTM D638 were prepared. This is the type 4 basically standard has been used, in which the dimensions have been mentioned. Now this is the samples that has been after the UTM testing in the tensile condition only. So this is I think really important for some of us. Whenever I am preparing some of the samples which are of some commercial use, I am interested in their mechanical property. Of course, that we have seen as a UTM testing. Then we are interested in their thermal property. So this is a graph that is showing us a thermal property of these type of the samples. This we actually got from a DSC setup, which is called differential scanning calorimetry. Now, this is interesting to see as a typical mechanical engineer. I am increasing the heat input from room temperature to 250, and then from 250 to room temperature, then again from room temperature to 250, then again 250 to room temperature. Basically, different heating cooling cycle. So in first heating, room temperature to 250, then first cooling, then another heating, then another cooling, right? So you can see on the x-axis, heating up to 250, then cooling, then heating, then cooling. Also along the x-axis, there is a time that is there. On the y-axis, I am interested in how much energy per unit gram, maybe in joule per gram, or if I am interested in some power in milliwatt, is there while in heating and while in the cooling cycle, endothermic and exothermic cycle. I am interested, right? So you can see I got some data whether my material is thermally stable or not. To understand this in a simple way, I give you one common life example. Suppose I go to the market and purchase two buckets, same company, same color, same dimension. One bucket I have put in my, let us say, bathroom, and the other bucket I have put on my rooftop. Now, what we observe that the bucket that I have put in a, let us say, closed environment in the bathroom itself, it may not have any deformation for a couple of years. There may not be any crack, but which is on the rooftop, it may have developed crack. Basically, in the, let us say, the daytime, lot of heat input was there. Then in the night time, maybe the once they have a cool environment, so amount of heat absorbed and amount of heat released may not be same, leading to some of the thermal deformation. So we have to manage the heat input to the heat released in that case. So that is one of the interest for us. Basically, from this type of diagram, we are getting basically four input. One is what is the peak melting. Second, what is the glass transition. Third, what is the crystallinity. and the fourth is the energy absorbed. These four things are typically of my interest as a material processing engineer. Now you can see in this case, once I was having a ABS, it was taking the heat as 190. Once I add 5% banana fiber into it, so basically the peak melting was increased. So that is really a good thing, that if I just add the agriculture waste into this, basically my peak melting is increased. And we try to see in the repeated cycle and we got a similar result. That means in the repeated thermal cycle, the material is going to behave in a similar way. And I can consider this reinforcement as a thermally stable reinforcement. Similarly, we observed it for the polyamide. So without reinforcement, the melting was at 217. So after that, it was at 225. And in the repeated cycle, again, it was similar. So I can consider that this type of material as really a thermally stable material. So some UTM testing for the load, tensile strength, elongation, spotted by their morphology. This we actually observed, and of course these were correlated with their percentage porosity, right? So some optimized values have been explored. Basically, the idea over here to explain is 3D printing is known to me. I am using right now the cartridge or consumable which are ready-made in the market. Why can't I have my own cartridge, which can be as per my resource availability? Like suppose if you are on the northern part, you have a different agriculture waste available. So that agriculture waste basically we can use for as a reinforcement into some of the thermoplastic, which can help two problems. One is the plastic solid waste problem. Second is the farmers may be advised not to going for just putting their waste on fire. They can be actually using for increasing some of the mechanical properties of the material. Like if you see in this case specifically, the percentage elongation after the reinforcement was significantly improved, right? So we can use these type of feedstock filament or the wire for tidying some of the iron bars, which can help me in roof construction in a big way. So there can be numerous application of using these type of 3D printed structures. Now, this is the another case study that I want to discuss with you for 3D printing part. Here, actually, we prepared a dry cell as an energy storage device. If you just see the cell, it consists of 4 zones in which there is some MnO2, there is zinc chloride and ammonium chloride electrolyte solution. Then you have a graphite and the zinc plate. So once we assemble all this, we get a chemical energy converted into the electrical energy. So what actually we did in this case was we use the different quantities of the reinforcement like the graphite powder, then zinc chloride and ammonium chloride, and then the MnO2. So these different combinations were put to a tester called MFI. This is basically a melt flow index tester, which is giving us the value in gram per 10 minute. You can take it as a reciprocal of the viscosity. In other terms, if I am having a high MFI, basically I can prepare the thin section. If I am having a less MFI, the preparation of the component for the thin section is really a challenge. Right. So how it works? Basically, I have a barrel over here over which I put my material, then apply some load. Here is a temperature condition. Here is a die, and I am getting a very fine wire, which I weigh how much gram per 10 minute this wire is coming. So what we observed, once I am having 100% ABS, basically the melt flow index was coming as 9, right? So then I go on adding the reinforcement like graphite. So once I put 90 and 10, the MFI was significantly reduced. Here just I want to tell you, for the commercial open source printer, the MFI value from 2 to 3.5 is really acceptable. I need not to change any hardware or the software of the system, and I can well print, with this MFI. So we go on trying with a different weight proportion, and we got a wide range or the variation in the MFI. Right. So initially it decreases, then it start increasing, then it start decreasing. There is a separate study at the material science why this behavior is there. Similarly, we try to observe for the zinc chloride and ammonium chloride, and similarly for the MnO2. You know, I need a high quantity of the chemical or the powder, which can really help me in getting a better charge value, right? But I have to be, very careful about the MFI, so that this can really help me in printing. So as I am increasing, so highest value I got over here, right? So in this case, this was really not required because I need to change the hardware settings. So similarly on this, we selected something in between, that is 65 and 35. Then we printed the disk. You can see the printing going on over here. Then these were assembled, and we got a output. Initially, once we assembled and like this, and we put some copper wires to get a output, the charge voltage was not observed. So we put some drops of the acetone at the interface, and we suddenly dissolve the interface, and finally we got a good quantity of the charge. The idea over here is what we observed. This zinc chloride and ammonium chloride blend disk is normally consumed as compared to the rest of the disk. So if I print a cell like this, only the consumed part I am going to replace, and rest of the parts are as it is. I can use this cell for a longer duration of time. We did the thermal analysis like I explained in the previous case, and what we observed in the repeated heating cooling cycle, like from room temperature to 300, then coming to the room temperature, my cell was stable up to 95 degree. Whereas our commercial cells are, giving us the desired output only up to the temperature of 55. Right, so we were able to use 40% of the plastic solid waste, and then I can use it at very high temperature. The third important thing is, with the 3D printing, I am getting a design flexibility. And now the startup things, like in this case, can be, think of preparing a cell like a sticker. So one layer of one material, then second layer, if one particular is consumed, you can just peel it off and then think of printing. Right, another layer I can put like a sticker. Then if I'm interested in higher charge value, basically I have to increase the volume over surface area, so I can think with the similar battery using a sticker type cells. So that can be the another advantage of preparing energy storage device like this. Now the 4D part, this is derived from a very simple experiment of the first year in my BE program. You see, here what we did is we printed some layers like this. Here is a non-conducting layer, then the conducting layer, then the non-conducting, then the conducting, and then the non-conducting. Basically, the idea is to print like a multi-material. So some non-conducting ABS or polyamide, whatever nylon you can use. Then for the conducting, this has been reinforced with graphene. Then the ABS or nylon, then with graphene. So I got a multi-material printed component. So what I did is, we allow the flow of the current in a particular direction. DC current was used. So once the current was flowing in this direction, so we are able to get north and south. Similarly, here again the north and south. So what will happen if the situation is something like this? There will be attraction between the north and south. So I will feel a compression, right? So now I am interested in expansion. So I am changing the direction of the current. So here is the south and south. So there is a repulsion. Basically, I can think of making a transducer which is 3D printed. Now it has numerous application I will just share with you. Now this is something 4D because I am using a stimulus, a magnetic field, and every time a controlled expansion or the contraction I am getting. As a mechanical engineer, we are quite comfortable with a material removal process that is called ultrasonic machining. Maybe for some of the students who have not studied about the unconventional machining, this may be a new process. Just let me explain in 1 minute how it works. I have basically a transducer over here, which converts some electrical energy, electrical input into mechanical vibration. So these mechanical vibrations are amplified using some design of the amplifier. This is basically, there are some different design like cylindrical, conical, so that the vibrations are focused at this end. Now here is a tool, here is a workpiece, and there is a gap between the tool and the workpiece. The tool is actually not in connect with the workpiece. Now what I am doing is I am putting some slurry, which are abrasive particles immersed in water, and I am supplying in between this region. Normally in ultrasonic we have a 20 kilohertz input. So at that high frequency, so these abrasive particles, once they strike with the tool, so with the high frequency there is these abrasives strike with the workpiece and we get a depression. So whatever the shape over of the tool is there, that is converted into the cavity over the workpiece. Now the idea over here is the electrical input converted into the mechanical vibration, and finally I am getting a the depression over this workpiece, and I got a replication of the tool shape over the shape of the workpiece. If you see the commercial manufacturer of this type of machine, so they provide the transducer, like one of the example is the Sonic mill. This is a US based USM setup over which I have worked. If you are interested in purchasing the transducer, this will cost us something $10, right? But if I make my own transducer like this will be something around 70 to 80 rupees, and I can get a similar result with this type of situation. So this can be really one of the startup or new product development for making my own transducer using these alternative printed 3D printed layers, and I can think of getting any shape. If I am interested in getting the higher value of the current, or maybe the compaction or the expansion, I can think of changing the thickness of the conducting and the non-conducting layer. Then with this input I am able to convert electrical input into the mechanical vibration. Now the other important thing to understand over here is about the tool over here. Now this tool that you are seeing over here is basically another constraint for the manufacturing engineer. This tool is also consumed because the abrasive particles, once they strike with this, you can expect that there will be erosion over the surface. And the tool life is a challenge. The people talk about using a tool material which can help me in getting a better tool life. Now to have a better tool life situation in this case, I can think of the extraordinary length of the tool, maybe a longer tool, so that once there is a erosion over the surface, you can think of machining it and then using it again. But the problem is, if you are using a larger tool, right? So what will happen for that tool? Basically, the machine shows it over. If the weight is more than 150 milligram, there is a auto cut in the machine. So what we actually did is to reduce the weight and to have a better tool life. We 3D printed this tool. So this is a 3D printed tool. This is basically the tool head, and we divided this tool into the 3 zones. Like this zone was having a Al2O3 particles reinforced in polymer of the coarse size. Here the Al2O3 particles reinforced in polymer of relatively fine size, and here were the super fine size. Then these, three different zones were used to do the drilling over here. So what we expected out of this was the combination of broaching as well as the, drilling together. So this is really a advantage that you can get only with the 3D printing. So these type of tools are available in market. You can think of making a form tool and do these type of combinations. Okay, some of the another thing that we can do for developing our startups is like in case of the commercial 3D printing, we have a nozzle like this. So once we print my component, I got a output in the form of ellipse. This is basically because of the Barrows effect. But the Barrows effect says that if a thermoplastic material I am printing, so the output something comes like this, right? So the stacking of the layer is like this, and you can see there is a air gap. Now because of this, I need to do some post finishing operation. So now what actually we did is as a startup type thing, we innovate on the nozzle, and in place of making this as a round, we basically make some structure like this, some convex structure. So because of the Barrows effect, we can get the result like this. So the stacking of the layers in this way. Then the second layers, we have a motor basically which change the nozzle in another direction. So the second layer is deposited over the first layer like this. So now in this case, you can see there is a less air gap. So better, post finishing type situation can be there. Similarly, in another way, if you are having two nozzles or three nozzles, you can think of making the nozzle design a innovative nozzle design in which layers like stacking in this way, then one layer like this, second layer like this, so that there can be a better control of the air gap. So these type of things can be really used. We can innovate and develop our new product. Okay, before I conclude my discussion, one of the 4D actual application on some innovative structure I want to share with you. Now, this is the real application that we have done in the some innovative structure for the 3D printing. This is on the some heritage structure. This is the project that has been under the SHRI program, Science and Technology for the Heritage Structure by the DST, Government of India. I'm interested in some preservation of the heritage structure. Now, if you see, as per the schedule by the CPWD, the structures, heritage structures are classified into three grades: grade 1, grade 2, grade 3. Grade 1 structures are those which are, under the control of Government of India, like Taj Mahal. Normally, the preservation is by the Archaeological Survey of India, and it is really difficult to work on these type of structures because of the lot of protocols are there. Then the grade 2 structures are under the control of, again, maybe the Archaeological Survey of India through Government of India or some state, governments. But it is again a lot of protocols we have to follow. Then there is a grade 3 structure, which is of course a heritage structure, but not under the control of government. Normally the private properties are there, and people are, working on these type of structures for, as a proof of concept, and then finally it is transferred to the, grade 2 and grade 1 structure. Now, basically, the difference is before the 19th century, once we were not using the cement in a way we are using right now. The structure cannot be used like if every structure is requiring some maintenance as the time lapses there. So, but if I am interested in some assembly at some suitable time, with the like some crack propagation is there, and I'm interested to fill those cracks, right? But this cement I cannot use for that structures. Now, if you fundamentally see how the cement is made, basically I have a limestone CaCO3. I heat it up to 1400 degrees Celsius. Then there will be calcium oxide plus CO2. This calcium oxide, once it is mixed with alumina, which is called clinker. So once I crush this and add some gypsum into it, basically I get a cement. But in the heritage structure, this is not done like this, right? So I am interested in providing some innovative solution for the preservation of this type of the sites. Now, what can be the problem? Right, suppose this is some heritage structure, this is wall of the structure, and the crack is something like this. So I can fill this crack not by the cement, but there are some solution which are epoxy based solution provided by one of the company called Hilti. This is a German based multinational company. We normally fill the epoxy into these type of the cavities. Now there can be a situation when the entry side of the crack is large and rear side it is small. I can again fill this. Then there can be a third situation when the entry is small, but on the rear side the crack may propagate upward or downward. Then filling this type of epoxy is not good. So what can be the solution? I am interested in putting some smart material into this, which once entered into the cavity, it is basically the uh, uh, compressed in size. So once it is there, then I give a stimulus. So this is basically a expanding and taking the shape of the cavity. So for this purpose, what I am doing is first the crack detection using a 3D laser scanning. I am interested in finding the geometrical volume of the cavity. So once I know the volume, I can think of printing a smart material which is reinforced, and then finally the assembly. Actually, we got this idea from a simple workshop, Maruti workshop. If you go to the workshop and for the maintenance of your vehicle, the first thing they do is they lift the car on a, let us say, some platform which may be pneumatic operated or the hydraulic operated, and the mechanic basically removes your all the tires, right? So they have a pneumatic gun in which you can change the direction of the flow of the air, maybe in clockwise or the counterclockwise direction. And finally we were able to unscrew or screw the tires by the flow of the air only. So air pressure is changing maybe in a way in a clockwise or the counterclockwise direction. I can screw or unscrew my nut and bolts. So similarly, once I am interested in filling the cavity inside, I'm basically squeezing it. So once it is entered, I am giving a stimulus and it is taking the shape of the cavity. These are some of the structures over which we are working. Like these are all British period, bridges. You can see over here. Here is a structure where the lower part is under the compressive load, and here is in this composite itself, the upper part is under the tensile load, but the composite is same, right? We are interested in maintaining these type of structures. This is the another location over which we are working. Its name is Sarai Lashkari Khan. This is on Lahore Delhi National Highway, something around 13 kilometers from Ludhiana. This was built in 1592 by a Mughal general. His name was Lashkari Khan. So these are some of the structures. Now I will give you some proof of concept. So for the proof of concept, basically what we did is we use three different materials like HIPS, ABS, and PLA. HIPS is one kind of a polymer, high impact polystyrene, acrylonitrile, butadiene styrene, and polylactic acid. So we measured their MFI. This is the observed value. This was something around 7.5. Then standard deviation, standard error were calculated. What we observed in case of HIPS, the MFI was 7.5. In case of ABS, the MFI was 8.7, and in case of PLA, the MFI was 13.52. That means if I use these three material for the PLA, I will get a more fine structure. Then we try to see their Young modulus. In case of HIPS, it was 112. In case of ABS, it was 175, and in case of PLA, it was quite less. Similarly, we observed the other properties like yield stress, glass transition temperature, their peak load, peak strength, peak elongation, these type of things, and we try to print this component on a 3D printer. Some of the parameters like the dia of the nozzle, dia of the filament, layer height, some default printing, infill pattern, perimeter speed, travel speed, extrusion temperature, print bed temperature, all these things were kept constant. So what we did as a different is we print as a multi-material with a different combination. Like in this case, ABS first, PLA middle, hips last. So in another case, hips in the center. In another case, the ABS in the center. And we did some input on infill percentage, their printing speed, and we try to print the tensile sample, something like this. Like you can see in this, the PLA on the top, here ABS on the top, here hips on the top. This is basically a stress strain diagram. Once I have a single material, tensile coupon, like for the PLA, similarly for the ABS, similarly for the hips. Then for the we also did their thermal analysis, like heating, cooling cycle. And what we observed, like this PLA was the most thermally unstable material as compared to the rest of the thing, right? So we try to see their stress strain curve on a typical UTM, and we try to establish the area under the each curve for getting the value of the modulus of toughness. Then we try to have the microstructure part. Now you can see this is a ABS layer by layer stacking. You can see this is at 30x magnification. Similarly for the PLA, we got some stacking of the material. Similarly for the hips, you can see there is a layer by layer deposition. Now what I did is, in this case, I printed the ABS first and the PLA on it. So what we observed is there is some side flow of the material, some globule formation was there, and once I did the reverse, like PLA on the base and hips in the middle, there was no such side flow of the material. Now if I compare this curve 1 with curve 4, you can see here for the curve 1, this blue color curve, this is the area under the curve, and this is for the sample 4, this is the area under the curve. So we can well compare that the modulus of toughness is much better in the curve 4 or the experiment 4. That means this situation is better if I am interested in getting better modulus of toughness of the material. So this is another important advantage that we got, that if we are really interested in better properties, then in case of multi-material printing, we can think of using these type of material for printing application. Now you just imagine the same arch type structure in which where I need a better compressive property, so I will put that on the lower section, and on the top where I need a better tensile property, I will put on the other side. So this is the way how we actually proceed for the multi-material printing of these type of the components. So these are some of the basic case studies that I want to share with you. We have some more case studies, but I believe that these will be sufficient for the starting purpose. Now I would like to answer some queries if are there with the audience. That's the some basic things from my side. Any question from the audience, I would like to answer.
Sir, I had a query regarding FGMs, so functionally graded materials.
Yes, please.
Yes, sir. Will we use a different set of binders for different layers, or a same binder can be used for manufacturing a whole functionally graded material?
Basically, like if I am using a technology of FDM only, the binder is actually not there. We are using the temperature.
Yes,
right?
sir.
So what we
Here
can
you
do
can
is,
SLS.
yeah, but if we are interested in in FDM only, I can think of getting a better property with a different heat input, right? So that can be the one of the way to get a better bond strength, right? So if you are
Yes.
using some adhesive based 3D printing, we can think of getting the concentration of the binder as the parameter.
Yes. Thank you, sir.
All students, if anyone has any query or any questions, you can unmute or write in a chat box, please. Even faculty staff, एंड स्पेशली 7th सेमेस्टर स्टूडेंट्स, अगर उनकी कोई क्वेरी है तो प्लीज उन्हें अनम्यूट करके जरा करें आप. Anyone has any query regarding 3D printing?
We have the facility for polymer, metal, as well as bioprinting. Being a national institution, if you want to use those facilities, all are welcome.
Sir, this is in mechanical department, na?
Yes, in
NITTTR.
Yes.
Okay. And even the facility of robotics is also there?
Yes, it is there.
Okay, sir, thanks. So students, if you have any query, you can ask. You are most welcome by writing in the chat box or unmuting yourself. Okay, Mandeep? Anyone? Mandeep Duha? हाँ मनदीप, किसी को क्वेरी है तो पूछ लो, और अदरवाइज वी विल फिनिश इट बाय जो भी आपका नेक्स्ट जो भी है वो करें आप, और फीडबैक लिंक डाल दें उसमें चैट बॉक्स में टू गेट द सर्टिफिकेट. ठीक है. ऑल आर रिक्वेस्टेड टू फिल द अटेंडेंस ऑब्लिक फीडबैक फॉर्म सो दैट यू कैन गेट द सर्टिफिकेट ऑफ दिस. ओके. हेलो. Mandeep?
Now we come to the end of this lively gathering. I just Preet Kaur from 5th Sem Mechanical Branch is here to present the vote of thanks. We hope you all had an informative session. On behalf of the organizing committee and audience, I thank the guest speaker, Dr. Rupinder Singh, Professor and Head Mechanical Engineering, NITTTR Chandigarh, for all the valuable information he shared with us this present time. A big thank you to Dr. Samir Sharma Ma'am, Principal, GCET Jammu, for gracing today's seminar. I extend a very hearty vote of thanks to the guests that spare time from their busy schedule to grace the occasion. I thank Dr. Amresh Kumar, Vertical Head Manufacturing Engineering at ACIC-RISE Association, and Mr. Sonu Kadam, Young Professional Aim at ACIC-RISE Association. I would also thank to our beloved HOD E.R. Sanjeev Gupta, Coordinator, Royal Mechnocrats, that has made this seminar a grand success through his motivation and dedication. Finally, I thank the wonderful students who have turned up in such a great number, not only from our department, rather from other departments of the institution. Thank you so much for your cooperation. Once again, thank you to all of you. Thank you for joining.
Hello. Am I audible?
Yes, sir.
From on the behalf of Mechanical Engineering Department, myself Sanjeev Gupta, I thanks Dr. Rupinder sir, Amresh sir and Sonu sir for such an event. We are very thankful to you, Amresh sir, for providing such a platform.
Thank you in fact
Sonu
to
sir,
you sir.
आपको भी बड़ा thanks, and
you,
you
sir.
provide a very knowledgeable session, Rupinder sir. और हम चाहेंगे कि ये हमारा ये जो एक अभी एक आज से जो रिलेशन स्टार्ट हुआ है ये आगे चलता रहेगा, सो दैट वी विल कॉल यू अगेन एंड अगेन फॉर सम इनोवेटिव सेशन सर. थैंक यू सर. जब भी आप कभी जम्मू में आए तो कॉल करें, हम आपको वहाँ कॉलेज में इनवाइट करें. अभी तो कोविड है तो अभी इनविटेशन देते अच्छा भी नहीं लगता, बट व्हेनेवर द सिचुएशन इज राइट वी वेलकम यू टू आवर डिपार्टमेंट. Thanks, Rupinder sir. Thanks.
Thank you, sir. Thank you very much.